following equations that govern the cooling tower operation. According to Perry, 1997, in order to predict the tower performance, it is necessary to know the required tower characteristics for fixed ambient and water conditions. The governing equations for tower characteristic determination are the Merkel equation, Chebyshev method, use of the nomograph, and the L over G ratio. The most accepted theory of cooling tower heat transfer process is the Merkel equation, or equation 12-8 in the Perry 7th edition. The analysis was based upon enthalpy potential difference as a driving force. The right-hand side of the equation shows terms which are related to air and water properties and are independent of the tower dimensions. Evaluating the integral term will then determine the tower characteristic. Another method that is normally used to determine tower characteristic by numerical integration is the Chebyshev method, shown by the equation below, which considers 4 points in the graph that was shown previously. The tower characteristic is shown in the graph as the area under the water operating line, which is shown by the red shade in the graph, which is the curve A, B, C, D. Another method known to be quicker but less accurate method is by the use of nomograph, figure 12-13 in Perry's 7th edition. The L over G ratio is another important parameter because the tower characteristic is affected by it, as shown in the graph as the slope of the air operating line. It is shown by the equation below. The L over G ratio for mechanical draft towers are normally within 0.75 to 1.5, and the tower characteristic values from 0.5 to 2.5. And for the design of a countercurrent induced draft cooling tower is also important because it is the most common type used and is thermodynamically more efficient type of induced draft cooling tower. In terms of sizing, the minimum area required for a given performance can be obtained in Figure 12-14 from Paris Chemical Engineering Handbook 7th edition, where the relationship of the hot water, cold water, and wet bulb temperatures to the water concentration is shown in the graph below. The following figure, Figure 12-15, also gives the horsepower per square foot of tower area required for a given performance, which is also known as the horsepower chart, which is also shown below. Aside from the determination of the tower performance and designing the tower, makeup water requirement or water makeup is also an important parameter. It is the summation of evaporation loss, drift loss, and blowdown, as shown by the equation below. It can be calculated by the summation of the said parameters. In the cycle of concentrations is also known as the ratio of dissolved solids in circulating water to dissolved solids in the makeup water. An example of this is the ratio of chloride content of circulating and makeup water, since chloride remains soluble in concentration.